So good afternoon. I feel lucky to be here because I missed my flight, but I made it. So Alec and I budgeted 2 hours for this tutorial, and it's 2 hours and 15 minutes. So if you have questions, you should feel free to ask them. Okay, so the slides and the long references are all at hunch.net. So you can go, you don't have to try to copy down references as we go through things. All right, so let's start with the supervised learning paradigm. Supervised learning is kind of the bread and butter of machine learning. It's where most of the economic value has occurred. So in supervised learning, what happens is you start with some training examples. So it's a pointer. All right, so you have training examples with, so this is what the data itself looks like for MNIST. And then you have labels. You hire some labeler to say, that is a 3, and that is a 5, and that is a 2, and so forth. So this is the standard way things are done. And now you turn that into you put that into a learning algorithm. I guess neural networks are the rage these days, but it could be a support vector machine, could be many possible boost decision tree. These are all possible supervised learning algorithms that see a lot of use. And then out comes a digit classifier. So you input the unlabeled data and you get out the label. So this is the standard way of doing things. This way works pretty well. So it's been used to solve speech recognition. That's an important big one. It's been used to recognize objects and images. This is a bunch of images from ImageNet. Now let's go one step beyond. Let's say we want to recommend news articles on some big website. Okay, so what's going to happen here is we're going to repeatedly observe some features of the user in the articles, and then we're going to choose a news article. We're going to observe whether or not there is a click, and then our goal is going to be to maximize the fraction of clicks. So it seems very straightforward. It's a small adaptation from supervised learning because we could take the click or not and say, oh, that's a label. So let's think about how we would try to solve this as sort of a supervised learning approach. So in a supervised learning approach, we would collect a bunch of information. So there'd be this user visited the website, they saw this article, and then they clicked or did not click on each of the individual articles. And then we would offline build some features of the user in the article. We'd build some predictor of the probability of click given the features of the user in the article. And then we would act according to the argmax over our articles of the probability, predicted probability of click given the features of the user in the article. Okay, so that's straightforward. And we would deploy this in an A/B test for maybe a couple weeks, and then it would fail, right? And the question is, why would it fail?
Because you're learning the old distribution that worked 4 weeks ago.
Yeah, that's a big one. You're learning the old distribution that worked 4 weeks ago. That's true. And particularly with news articles, an article's interest level decays rather rapidly. So after a day, an interesting news article is maybe, okay, and 2 days later, maybe it's old news. So that's an important one. But there's another one which is even more important.
You didn't tell us how the first step happened.
I didn't tell you how the first step happens. Yeah, that's right. And that's a very important bit. Okay, so the question is what goes wrong? Okay, so suppose You had the opportunity to present a news article about Ukraine to John. Would this be interesting to me? So it seems kind of oddball, but it actually would be interesting to me because my wife is from Ukraine. And, there's a fair amount of keeping track of what goes on there. Okay, so we can think back to the original supervised learning paradigm where you have a labeler who labels things. And the question is, can a labeler even know this? And the answer is probably not unless they know the person browsing the website personally. Right? And then we can think about the hack that we did, where we just collected a bunch of user article click information and pretended the click was a label. And then the question is, does this give us the information that we need in order to learn that John is interested in news articles about Ukraine? And if you did not display any news articles about Ukraine, then that's not in your information here. And so there's no way to gather there's no basis for good judgment. You have the wrong signal information, either as a labeler or as an existing system that does not display news articles about Ukraine. So that lack of information is kind of critical. And then the other one was what we discussed earlier. The model value decays over time. So this is using real-world news article recommendation, where you take the model for day one and then you display it on day two. And you ask, what fraction of the value that I could get by training in near real time do I achieve using a day-old model? And the answer is about half. So these are kind of two very critical reasons why the A/B test fails. Okay, so let's think about interactive learning for a minute. In interactive learning, the features are going to come from the world to the learning algorithm. Maybe that's the user history and news stories. And then the learning algorithm is going to choose an action. Maybe that's selecting a news story to display. And then there's a consequence, which is maybe a click or not, or it could be something more complex than that. In general, we're going to want to boil down the consequence into some sort of real valued scalar reward. So I'm assuming most of you have seen this kind of loop in a reinforcement learning setting and in an active learning setting. We'll be discussing those in a moment. All of these have this kind of shared interactive property. And this tutorial is really about how you can master that shared interactive property and solve real-world interactive learning problems. Okay, so there's two more reasons beyond the two that I started with for why I think you should be interested in interactive learning. One of them is that ignoring click information just seems wrong. And in fact, you could save a lot of money by actually taking advantage of the interaction information which is just there. The other one is, I think, related to AI. So I would actually like to see a show of hands. Who thinks that AI is a function programmed with data? There's some people. 2 people at least. Okay, so that's some people. I think people are cautious because this is the first one displayed, and that's never the right one. And yeah. But nevertheless, this is, I think, the conventional answer at the moment, because AI is deep learning. Deep learning is typically a function programmed with data. I think this is a lowering of expectations compared to what I thought of as AI when I was growing up. And of course, there's artificial general intelligence. I don't mean that. I just mean, can we call something intelligent? And I kind of feel like static functions don't do it for me. I think that AI should be an economically viable digital agent that explores, learns, and acts. So this is closer to what my internal idea of what an AI is than a function programmed with data. Okay, so there's several different flavors of interactive learning. Let's kind of go through them a little bit. The first one, which is very common, is just full-on reinforcement learning. And in full-on reinforcement learning, you have the same loop that I showed you before. You have the same reward signal, but the reward that you observe may be dependent on many previous actions, right? That's going to be a critical distinguishing element. So the thing which is interesting about full-on reinforcement learning is that first of all, it has been used to solve some really fun things. So there's a lot of games that have been addressed effectively with full reinforcement learning. One thing that's important, though, is that you really need to have a special domain, and you really need to have a very large sample complexity to solve things with full-on reinforcement learning. So as far as special domain goes, I have a collection of a couple simple reinforcement learning problems, which will basically break every existing full reinforcement learning algorithm. And in terms of sample complexity, well, I think that you're not really even starting out until you have about 10 million samples. Right, so you definitely get the right signal to solve things in terms of the reward. Often you don't have enough of that reward signal because you need a very large sample complexity. Dealing with non-stationarity in the world, I think, is actually kind of difficult in a reinforcement learning setting because the number of samples required tends to be so large. It's often an adventure with many PhDs and data scientists to solve a reinforcement learning problem. And, you know, it satisfies my definition of AI. You're doing interactive, you have an agent that is kind of learning and exploring and acting in the real world. So in the other extreme, there's active learning. In active learning, the learning algorithm is choosing which examples to label. Right, so this is a very straightforward modification of supervised learning, where instead of having the labeled examples chosen for the learning algorithm is kind of participating in that process. So that's nice. This has the wrong signal problem. That's kind of an issue. So a labeler cannot know whether or not I would be interested in a news article about Ukraine. It doesn't deal with non-stationarity, and in particular, I would say active learning algorithms often don't work particularly well if the problem itself is non-stationary. It definitely can reduce the number of labels required, so that's good as far as saving money, and it's still, somehow it feels a little bit too simplistic to be thinking of it as AI. Okay, so then in between, there's Contextual Bandits, which is what this tutorial is going to be primarily about. So this is the same setup, more or less, as full reinforcement learning, except that the reward is directly associated with an action in a context. So there's no guesswork about which action in which context led to which reward. So that seems like a minor simplification, but it ends up being a huge simplification as far as the theory goes. It's no longer the case that there are a few problems which are obviously solvable and yet easily break contextual bandit learning algorithms. In fact, the degree of tractability is similar to what it is for supervised learning. And we'll discuss that in a bit more detail in a moment. So if we compare, you have a right-ish signal. So what I mean by this is you are using a short-term immediate reward. And in many problems, we can find some sort of short-term immediate reward, which is a good expression of So in a reinforcement learning sense, this would be the advantage that you get by taking an action. So we want a reward which is going to be a short-term reward which is going to be well aligned with a long-term reward. Non-stationary is okay, it's because the sample complexity is okay. And we have tricks for dealing with non-stationarity, which Alec will get into in more detail. You don't need labels at all. You're just using the interaction information as it occurs. And yeah, this is actually an economically viable digital agent that explores, learns, and acts. Okay, so let's go through a few more scenarios where you might want to use this kind of approach. Another one is kind of wellness. So you want to give people advice about what they should do in order to develop healthier habits. So in this scenario, maybe you observe features of the user and the advice, you choose some advice, and then you observe the steps walked, and your goal is to achieve a healthy behavior. So this is a good example. There's actually a number of different examples. The news article recommendation is something that I was involved in a long time ago. There's add choice, there's add format, there's education, online learning, the other kind of online learning. There's music recommendation, there's robotics, and then there's a lot of work on wellness and health. So all of these are using some sort of near immediate reward or directly immediate reward reinforcement learning in a contextual bandit paradigm or something extremely close to that in the way the problem is formulated. Okay, so these are, all right, what does this say? It says that the primary takeaway I want you to get from this is that it's a good fit for many real-world problems. I think that if you look into real-world problems, things that are actually solving applications that control something in the real world, that are actually learning effectively from that interaction information, this is the dominant paradigm. Okay, so let me tell you the outline. So I'm going to start with an overview of the algorithms and the theory. This is not the primary point of the tutorial. The primary point of the tutorial is how you make this work in the real world. But this is necessary as a foundation for you to understand things in greater detail. So in particular, I'll be talking about how you evaluate, how you learn, and how you explore. And then Alec is going to take over. He's going to talk about things that go wrong in practice. He's going to talk about systems for going right, how you make sure that these problems don't happen. And then he's going to talk about experiences from doing it in practice and tricks to avoid some issues that come up. Okay, so the setting we're going to work in is Contextual Bandits. In Contextual Bandits, you repeatedly observe some features. We'll be using X to denote that. You choose an action, A, and then you observe a reward, R. So your goal is to maximize the expected reward. And then the critical difference from full reinforcement learning is that we know this reward is associated with this action in this context. Okay, so we're going to try to find a policy which, let's go back, which given the features chooses the action in step 2. So I need to define a policy for you. A policy is something which maps features to actions. So that could be a neural network. Maybe you have 2 possible actions. You compute the value of each of these units in the neural network, you take the argmax, and that's your policy. Or maybe it's a decision tree, using the features, you descend to some leaf, and the leaf has some action in it, and you take that action. So a policy is essentially just a classifier that acts. That's all it's really meant by policy. All right, so one thing which is critical is gathering the information that you need in order to succeed. To gather the information that you need in order to succeed, you need to explore. There's several ways to explore in general, but for contextual bandits, there's really just one way, effectively, at least for the kinds of things that we want to do. We're going to use random exploration. So there's a user that comes to a website, there's some policy which will choose a space story for them. And we want to have some control over that action. So when I say randomized, I do not mean uniform random. We're going to do something non-uniform in general. But it's important that you have some support on the actions that you're going to choose from so that the learning algorithm has the information that it needs in order to learn that John is interested in Ukraine. Right? And it need not be the case that, how do I describe this? Let's go back a step. So this set of features X can be very large and high dimensional, as we're used to in machine learning and supervised learning. Right? So when I say exploration, I don't mean that for every X we try every action. That would be crazy. I mean that there is just some distribution over the actions given the features. And so there's some probability of choosing the action that you might be optimal for every individual X. Okay, so you randomize a little bit. Maybe you get a news article about food instead. And then based upon this information, we'll be able to do many of the tricks that we want to do. We'll be able to learn in a manner which allows us to succeed. Okay, so the first question that you wanted to address with exploration information is evaluation. Given that you have some experience, so now we have the features, we have the action, we have the probability of taking that action because we're exploring, and then you have the reward that was realized when you took that action. So we have a bunch of these. We have a set of these quads. And then on the side, we have some policy, which maybe we developed afterwards, that maps the features to an action. And the question is, how good is the policy? So in normal usage, what you do at this point is you go and you deploy things in an A/B test. And then after 2 weeks, you get some information about how good the policy is. So basically, in the normal approach, you ignore this information, and you deploy in an A/B test, and you get some information about how good the policy is. So that takes 2 weeks. It's not terribly good if the world is non-stationary. But it is a standard, and it does get used very often at internet companies. In supervised learning, on the other hand, the approach is very different. In supervised learning, what happens is you have your data. Maybe you split it into 2 parts, one for training, one for testing, and maybe this is the test data set, and now you would just evaluate the policy offline. Right? Maybe that takes a minute. So it's a huge difference in the amount of effort required and in the ability to evaluate a policy. So the claim is that for contextual bandits, it's basically the same as a supervised learning paradigm in how you can evaluate. So in particular, the simplest form of offline estimator, which is IPS, takes an empirical average over our experience, the features, the action, the probability of the action, and the reward. And then we're going to say, we have a good policy if the reward is large. And this is an indicator function, so it's a 1 when the inside is true and 0 otherwise. So it's, and the probability, the policy's chosen action is equal to the randomly chosen action when you gather the data. So the reward large is good, agreeing with the action is good, and then we're dividing by the probability. So that dividing by the probability is a little bit mysterious. That's kind of the propensity score. And I'll show you exactly why you do that in a moment. Okay, so there's a very simple theorem here. Oh, and by the way, I should mention that for each of these individual elements in the beginning, I'm going to show you the essence of things, and then this typically several ways to improve on that. I'll mention those, but the goal is to give you the foundation that you need in order to understand the second half of the tutorial. Okay, so the claim is for every policy and for every distribution over features and a reward, so this is a hidden reward vector, so there's an implicit reward which could exist for every action if you took that action. The expected reward of the policy's chosen action is equal to the expected value of this IPS estimator. So it says that the estimator is unbiased. And just to write that out, again, the expectation of the empirical average of the reward times the indicator function divided by the probability. So we can prove this very easily. We say for every choice of features and reward vector, we have an expectation remaining over the randomly drawn action because we're randomizing over the action. And I'm going to decorate the reward with the associated action and the probability with the associated action. And then I'm going to say, well, an expectation is really a sum of over the elements of the probability of the element times the thing inside. And I'm going to say, probability of action cancels with probability of action. And then the indicator function is going to cancel with the sum because only one term is actually on. And then you're done. Right, so this is a proof that it's unbiased for every individual point. And that means it's unbiased for an expectation over points with respect to any particular distribution D. Okay, so it is possible to offline evaluate, like you do with a test set in supervised learning, for contextual bandits. And that means that we can do things much more rapidly than with an A/B test. Maybe 3 orders of magnitude faster would be a typical estimate. You can also create a counterfactual dashboard. So this is actually real, this is not a mock. This is a real counterfactual dashboard of a system. The black here is the system's actual performance, and then the green here is the system's, is that green? I don't know. Anyway, this line is the system's predicted performance using a slightly more sophisticated form of this technique. Right? And then at the same time, on the same data, we can evaluate some other baseline policy's performance. Right? This is the time axis here. This is the value. Higher is better. Say again?
They're the same color, right?
Yeah, so the default policy, so everything in this color is a counterfactual estimate. So what I mean by counterfactual is not the history which is actually observed. So I mean using this, using IPS. So the black is what is actually observed, So if you just record the rewards that you're getting over time. And the other ones are these estimates according to this slightly more sophisticated than IPS approach. Okay, so let's talk about better approaches. If you can build a good estimator of the reward itself, that will allow you to reduce the variance. That's good. You can incorporate that. You can use that. One of the problems which can happen with IPS is, especially in the beginning when you have relatively few samples, your estimator might become, let's say our rewards are in the range from 0 to 1. Your estimator might go from 0 to 50 because the probability might be 1 over 50, and the reward might be 1, and then just mathematically you get 50. That goes away as you get more samples, but there's a technique where you divide by the maximum that you could get, which makes that go away faster. You can also, when the probabilities become too small, you can clip them. And then you have a bias variance trade-off, and that can be very advantageous in various evaluations. Okay, so let's move on to our next problem. The next problem is learning from exploration. Given the data that we require to evaluate, how do we maximize the expected reward of the policy chosen action? Okay, so now that you know that you can evaluate, you know in some sense that it's possible to do this because you could use guess and check. You could guess a policy, try it, guess a policy, try it, guess a policy, try it, and eventually that would converge to something useful. Now, it could be very eventual because guess and check is not a very good learning algorithm. So it turns out there's more direct approaches for using this information in order to learn. So the simplest one is based upon IPS itself. So we had a theorem saying that the expected reward of the policy chosen action was equal to the expected value of this IPS estimate. And if we look at the IPS estimate, the reward of an action is equal to R over P for the policy chosen action and 0 otherwise. So that means we could take our existing data and we could, for each action, if that action agrees with the action that was taken, we could say, this is R over P in value, and otherwise 0. And we know that would give us an unbiased predictor of the value for the actions that are taken. Okay, so this is almost a familiar form. You can go a little bit further. You can say, I'm going to have a new reward, which is 1 if the policy chosen action is A, and 0 otherwise. And then I'm going to take the R over P, and I'm going to put that into an importance weight. So an importance weight is a trick where you say, this example is R over P more important than a typical example. Okay, so now if you look at this closely, you see that you have one right action and a lot of wrong actions, which is exactly equivalent to multi-class classification. So this is just importance-weighted multi-class classification. This is a very simple approach that allows you to reduce contextual bandit learning to importance-weighted multi-class classification. Okay, so let's take a break from that. And for a moment, let's talk about VW. So the algorithms I'm talking about here are all in a toolkit called Reuploading. The toolkit has a BSD license. It's been around for 10 years. There's a mailing list. There's a bunch of people using it in various ways. It has command line, C++, C#, Python, Java, ICML, daemon interfaces, and it's used by lots and lots of companies. Interestingly, the the project has now been around much longer than many of the companies. Okay, so let's think about this for a minute. Maybe we want to do contextual bandit learning with VW. So this is the kind of thing that you would do. You would create an example. You say, my action is 1, my loss is 2. Okay, so critical difference here. VW operates on a loss basis rather than a reward basis. So you need to use a negative sign when you are using it. And then I have the probability of the action, which was 0.5 in this case. And then I'm going to have some features, and VW is kind of nice in the sense that you can shove in words as features, and it will use a hashing trick to turn them into indices and work with it. And then you want to feed that into VW, and you need to specify that you're doing contextual bandit learning, maybe with 2 classes. Could be more. Okay, so let's look at a larger data set. Okay, so here's a data set which is 132 megabytes gzip compressed. And if we look at the data set carefully, we see the same label format I just showed you. And then we see a bunch of words that are a little bit stemmed. And now we're going to plug in a command line. The command line is a little bit more complex because we want to do n-grams on the words, and we want to allow some skips between the words in the n-gram. We're going to use a cache file, just to make it a little bit faster because often parsing is a limiting factor. And then we're going to use a 24-bit hash rather than the default 18-bit hash. Then we can run through this, and we can see it chewing through examples. As it's going through the examples, it's doing this counterfactual evaluation. And you're getting an estimate of the performance. You can see that the loss is going down over time. So then at the end, we've gone through 781,000 examples. The average loss is 4.8%. This particular data set is a little bit artificial because it's derived from a supervised data set where typical linear learners would actually achieve about 5.1%. Typical supervised learners would achieve 5.1%. This is the RCV1 CCAT or not data set. Because of the n-grams and skips, we end up doing slightly better than that. If you're doing supervised learning on this with the same kinds of flags, you do slightly better than this, but the performance is actually very similar. So even though we're only observing the loss of an individual action, we're still achieving a performance which is fairly similar to what you would get with supervised learning. Right, so we get some reasonable performance here. Okay, so I'm going through this just to emphasize that you can really do this. You can really do offline evaluation. You can really do learning. Okay, so let's talk about other techniques. Policy gradient is an approach which can be used for contextual bandit learning. This is normally thought of as a reinforcement learning algorithm, but certainly can be used here. There's several other ways to reduce from contextual bandit learning to supervised learning. I don't think I want to go into details, except one of them is unpublished and actually I think often the best one. That's in VW. And then there's a way to use this weighted IPS approach directly, at least for some representations. Okay, so now that we have learning working from Contextual Bandit data, you would like to be able to evaluate your learning algorithm. And we kind of already have an answer to that because we know that we can evaluate a policy offline. And that means we could have a train set and a test set. We could train on the training set and we could test on the test set. Now the difficulty with that approach is that often you're actually in an online environment where you're gathering data over time. And so the performance that you get halfway through the data set, halfway through what would be the training set, matters in terms of how you want to value the learning process itself. So there's a basic trick here. You can use progressive validation. So I'll show you what that is. So suppose we start with some initial policy. We are going to test on the first example, and then we'll train on that. And then we'll test on the next example, and then train, and then test, and then train, and then test, and then train, and then test, over and over again. And so we're always testing one ahead of where we're training. So you can prove a theorem about this. You can say, the expected progressive validation value is equal to the uniform expected policy value. So you have 1, 2, 3, 4, 5, 6, 7, and so forth, different policies. Pick a random policy that has some expected loss rate or reward rate. And this process of picking a random policy and looking at its reward weight has an expected value as well, right? So that's what progressive validation gives you. And then you can also prove that okay, so if you have everybody knows that if you have a small test set, you don't trust the result very much. If you have a large test set, you trust the result quite a bit more. If you have a large training set, you may not trust the result because you could be overfitting in your learning process. So the critical thing about progressive validation is that it's like a test set. So if you have a large number of samples, you should trust the result in the same way that you trust a large test set. Okay, so we're on to the last bit. The last question is, how do we actually gather the exploration data? So the simplest algorithm is always epsilon greedy. It's always, well, it's typically not the best algorithm. But the simplest algorithm is with probability epsilon, you're going to act uniform random. With probability 1 minus epsilon, you're going to act greedily. Okay, so this is unsatisfying in a couple of ways. One of them is, you end up exploring alternatives that are just completely implausible because your existing data can rule them out. Another one is that, it's too simple. So there's a lot of better algorithms for doing exploration, and a lot of the work and research over the last few years has been on these better algorithms. So all the better algorithms have the property that they maintain some ensemble and they explore amongst actions of this ensemble. So there's different techniques for doing that. Thompson sampling is the very old one where you say, I'm going to update according to Bayes' law. I have a posterior. My ensemble is the posterior, is a draw from the posterior. EXP4 is a different exponential weights algorithm. These two are lots of fun because these two algorithms here are formally kind of linear in the number of elements, unless you're lucky. These are approaches which, given an oracle, can achieve the same kinds of regret guarantees, same kinds of theory guarantees efficiently. Okay, so when we try to do evaluation with progressive validation, this does not take into account the loop. It does not take into account the process of data creation itself. That's one of the critical things about interactive learning. You are creating the data that gets fed into your learning algorithm. You need to take that into account explicitly in order to stabilize the learning process itself. So, for example, if we go back to progressive validation, the best learning algorithm here, the one which achieves the best performance, is typically one which does no exploration at all. But that's not going to work, right? So if you actually deploy that in the real world, you start creating data which is very different from the data that you're using to train the learning algorithm, and then bad things will happen. So we want a technique to actually evaluate we want a technique to evaluate the entire loop. So the basic approach there is rejection sampling. You can start with an unlabeled sample as before. You can check to see if your policy chooses the same action as what was gathered in the real world. If so, you keep it. Then you can check with the next sample to see if your policy chooses the same action as what was gathered in the real world. If not, you throw it away. So you just go through this process of checking to see if the learned policy, so when I say keep it, I mean you actually take that sample and you train with it. So every red point here is one where we update, every green point is where we're evaluating, and every missing point is where we did not update our learning algorithm. So this is a more delicate kind of offline evaluation because it takes into account the full loop. Typically we use this when we're varying the choice of exploration algorithm, while if we're changing our choice of features or representation, we're using the progressive validation itself. Okay, so that runs along. Oops, too far. As a theorem, you can prove that the realized history is unbiased up to the length that you observed. So if you have a stationary world, which often you don't, then this process will produce a policy which is typical of what would happen if you trained on 1, 2, 3, 4, 5, 6 samples. So there's some better versions available. This is that rejection sampling approach is the key idea for how you can get an estimate of performance which is faithful to the data creation and consumption loop itself. Okay, so there's more detail out there. There's a tutorial that I did at NIPS which covers the theory in much greater depth. There's a class that I did at Cornell Tech this last spring. And then Alec is going nuts creating some really nice class notes for a class that he's going to teach at Columbia in the fall. Okay, so contextual bandits are a good fit for many real-world problems, but also there are fundamental questions that have useful answers. This ability to do offline evaluation, I think, is revolutionary for many people because it means that you don't have to wait 2 weeks. You can wait 1 minute to get an answer. The ability to directly learn from exploration data is incredibly useful because you don't have to apply guess and check. Effectively, what happens with A/B testing is you're doing guess and check in many cases. That's not a great learning strategy. So this is, who knows the tale of Goldilocks and the Three Bears? All right, so good number. So the girl invades the house of the bears, and she tries all the soups, and she finds a soup which is just right, not too hot and not too cold. I think that's kind of the situation we're in right now. Supervised learning itself is too cold because it doesn't deal with essential issues, doesn't deal with the need for exploration, and it doesn't incorporate that exploration information effectively. Reinforcement learning itself, at least full-scale reinforcement learning, where you have a serious credit assignment problem, is well, it's an adventure. And that makes it difficult to actually apply it in the real world, because often you need to be lucky in the choice of problem, and you need to have a large sample complexity. Contextual Bandits is kind of the happy in-between point. It's the Goldilocks point for interactive learning right now, because it has reasonable sample complexities. You can learn with a number of samples similar to what you require for supervised learning. You can use techniques similar to supervised learning, and you just need to adjust the way that you use the samples in various ways and the way that you gather the information in order to succeed. Okay, I'm going to hand this over to Alec.
Right, while we switch slide decks, if people have questions, feel free to ask. Yeah.
So there's this assumption that the reward is independent of the policy choices, which seems like a very strong assumption to me. You show me articles about Ukraine, I might get a soft spot for Ukraine and really crave these Ukraine articles over time. So to what extent, I mean, that reinforcement learning maybe covers that, but not contextual bandits.
Right, so in Contextual Bandits, there is definitely the assumption that your reward does not, your choice of action in response to a particular context does not influence the distribution over the future rewards that you're going to see. And in some sense, this may or may not always be completely satisfied, but you can think about it as a pretty good first-order approximation to reality in a large number of problems. And I think that's what sort of the broad number of existing applications to some degree that we are seeing is providing us empirical evidence that that's true. And we'll talk a little bit about, in the second half, about reward functions at some point, and I'll talk some of the practical issues that arise and how we might address them.
I have a really quick question. So in a lot of practical situations, there are a lot of business rules covering exploration.
Mm-hmm.
For example, you might want to just use this kind of a, say, multi-word testing paradigm for building a marketing system that doesn't surface people. And there might be campaigns running by marketing managers or people who use their intuition in parallel. So it's typically hard to generate a pure, a really exclusive exploration paradigm. Like I've been.
We'll get to this in a moment, actually. So, yes, I think I will address that question, and if I don't, ask me again. Yes.
With that point with the rejection, with the getting the could you please go again through the criteria for accept reject that?
So basically, you have a probability distribution, so you have an exploration algorithm. It takes in a context, and according to some distribution, draws an action. You have your offline logs, which may contain a different action that was actually chosen on this context. So if the two actions match, then you keep the sample, because then it's as if you acted according to the exploration algorithm you're trying to evaluate. If the two do not match, you discard the sample, and you just keep on waiting till you see a match. So that basically, if the exploration algorithm that you're trying to evaluate is very different from the data collection one, then you're going to basically see fewer matches. You're going to rightly have smaller confidence in your evaluation because there's greater variance in the evaluation. So that's, does that help?
Yes, thank you.
Okay. All right. So I'm Alec. Hopefully, John's got you all excited at this point about contextual bandits, about how they're great fit for many things. I'm going to be a bit of a downer. I'm going to start talking about practical issues and begin by talking about various things that might go wrong in practice before telling you about how to fix those issues. But just by way of a quick recap, hopefully John's convinced you that interactive feedback is plentiful, and it can be incredibly useful if we use it the right way. And we need to do randomized exploration to leverage this feedback. But if we do this randomized exploration, we can start answering questions like, given a particular policy, how much value it generates. Given some large parameterized class of policies, we can use supervised machine learning techniques effectively to find the best policy from that class and also generate an estimate of how much that policy's value would be. And we can answer all these questions completely offline without actually running any additional experiments online. And finally, we have exploration algorithms that are pretty sophisticated that make sure that you explore just the right amount. So you try all the things that you need to in order to collect useful data, and you don't go off trying things that you know are actually not going to be useful. And so really, if you put all of those things together, it starts to suggest a pretty powerful recipe for success where you, let's say you take your favorite contextual bandit algorithm and you start, you deploy it online and start basically doing randomized data collection using that algorithm. You gather your experience, and the experience, as we've talked before, looks like we have some features or context. We have chosen some actions from a probability distribution, and we know the reward of this choice. And we have done this for many, many examples, so we have a pretty large log. We can take this log, and we can answer a variety of questions offline, such as maybe I started with some initial choice of features. One of the things a lot of people spend time on is coming up with better features. We can, again, ask whether a new set of features helps or not. We can estimate the value of using a different set of features than the one we used here offline. We could try different representations. So maybe we started with a policy class parameterized by linear functions, but we could then swap it out with neural nets or decision trees and estimate the effect, the value, impact we get by doing this change. And we could even replace our exploration algorithm. So maybe we started by something simple like epsilon greedy. We want to replace it by something fancier. And we want to estimate how much that helps. We could use this rejection sampling idea John talked about at the end to evaluate this piece. So really, it sounds like what we might be able to do is we could take an application that we care about as a practitioner. We could hook up our learning algorithm with the application to exercise this online data collection and offline data analysis and data discovery part. You could almost get to the point where you could automate these online and offline improvement aspects so that you could put your feet up and just watch everything work. Now, obviously, if things were that simple, then we wouldn't need the second half of the tutorial, right? So I'm going to begin by going through some war stories. So these are really some example anecdotes that we've gathered through various experiences of trying to apply these techniques in practice. Us and our colleagues at various organizations, at various companies who've run into repeated issues of a similar flavor. So I'll take you some of the canonical failure modes that people might encounter. The first one I'm going to start with is actually pretty common and related to the question that was just asked. So John showed you this graphic before when he was talking about why we might need randomized exploration. So let's say we have this an exploration algorithm that saw this user and decided to display this news article about space. Now, sometimes what happens is that you have, in news recommendation, you have breaking stories. So maybe there's been a salmonella outbreak in candy, and an editor comes in and says, I don't care what your algorithm picked, you have to display this story about candy. So your choice gets completely overridden. You can't do anything about it. What you record in the logs is the story that the user eventually saw, which is going to be the story about candy. So now let's think about what's going to happen. Let's just carry out a little thought experiment here. Let's say the algorithm was going to pick the article about candy with probability half, the article about space with probability half. So we think we're picking the article about candy half the time. We're observing the article about candy with probability 1 in our logs because of the editorial override, right? It's going to be displayed to every single user all the time. So we have a mismatch here. Let's think about the impact of this mismatch for off-policy evaluation. So let's take a policy that would have picked the space-related story. And let's think about what would happen if we apply the IPS technique, the inverse propensity scoring technique, to that policy. So the estimator looks something like this. You look at what is the chance of observing the space story in the data. Each time you see the space story in the data, you pick up its reward, and you divide with the probability with which you would have chosen that story. Now, normally, when everything is going according to the plan, the probability with which you were planning to pick the space story and the probability with which you actually observe the space story in the data are basically the same because you're driving the exploration. However, we have a problem here that we actually never observe the space story in data. So this probability is 0, whereas we think the probability is half. So we just end up estimating pi's value as 0, irrespective of how good the story is. On the other hand, for the candy story, we think we picked it half the time. We picked it with probability 1, so we overestimate the reward by a factor of 2. What this means is that we cannot trust our offline evaluation anymore when these mismatches start happening. And this is, of course, like one data point, but you can actually simulate this effect at large scale. So we have some news article recommendation data from MSN, real data, where we actually simulated a failure of this form. And what we observe is that the offline and online estimates are just starkly different when you have this sort of a problem. Now, this is terrible because this means that the whole hope we had of getting high quality offline estimates of what's going to happen online, that story goes out the window. Okay, so the failure mode that's happening here is that we effectively, the probability that's recorded in our logs is not the same as the probability with which where the actions are being really chosen in the data. I'm not going to tell you how to fix this just yet, so there's some suspense for now. Instead, I'm going to tell you about a different failure mode next. When you're trying to predict something about future, it's pretty common to use the past as an indicator. So if you're trying to predict something about for instance, click probability on something in the future, it's pretty common to use historical click rates as a predictor. So what that means is that you have some sort of an exploration algorithm that receives a context from the application, and part of the features in the context includes the historical click rate, say, of every available action. Now, based on these features, you pick an action here. At some later point, you observe the reward. You observe whether the action was clicked on or not. And the important thing to keep in mind is that there might be a significant delay before you observe the click. Depending on the application, this might be hours, days, or even weeks. So it's only after you observe the reward that you can actually update your model with that information, right? You took an action, but until you find out what its quality is, you cannot update your model. So at the point where you're ready to update your model, what do? You need the features again, right? We need both the features and the reward to update the model. So you have some sort of database. You look up the database for what the click rates are on different actions because they are part of your features. And you, along with the reward, update your model. Now we have a problem here because maybe there was a day that elapsed between when you chose the action and when you update the model. And the click rates, the features, might have completely changed in this time. So effectively, it's as if you're working with the wrong distribution of data. And again, you can simulate this type of failure, and you again find that online and offline estimates do not correspond to each other anymore. So this is again giving rise to an undesirable sort of failure. Now, the third issue I'm going to show you is a little bit more subtle. So when people are doing recommendation type tasks, it's pretty common to look at conversions. So what I mean by conversion is I showed you recommendation for something. let's say a product, did you go and actually buy that product? Okay, so maybe you're looking to buy toilet paper. You search, I can show you one of two ads. The first ad is for discount to buy toilet paper from your local store that's down the street, or I could give you a discount coupon for buying it from Amazon. Perhaps if I showed you the ad about the local store, you would pick up the coupon now, but you would not actually go and buy it until later in the day or on the weekend when you go to the store. But if I give you the offer for Amazon, then you might just complete the purchase right then. So what we are seeing here is that we have different delays associated with observing the reward of different actions we might choose. And if we don't correct for this somehow, what will happen is that we'll keep on seeing much more information at any given point of time about the Amazon action than we would for the local store action. And again, this means that we will end up learning on the wrong distribution of our examples. This action will basically be overweighted in our learning distribution, even though it's not really the case that we see this action more often. And again, you can simulate this sort of failure, and you see that the online and offline estimates differ quite a bit. And while I'm saying that these are simulated failures, I want you to sort of keep in mind that the only thing that's a simulation here is the exact number about how much the online and offline estimates are different. These failure modes are very real. These are failure modes that many people have encountered in practice over and over again. So these are very real things that we need to keep in mind when trying to use contextual bandit algorithms in practice. And in fact, we could actually stay here for much longer, going through one failure mode after another that would come up. And when these things happen, it's actually incredibly frustrating because often you've spent a really long time, weeks or months, working with an application that you care about to integrate some contextual bandit algorithm that you're interested in trying out. You do the integration, you wait for data collection to happen, you get the data set, and then you find out that your data displays one of the bugs that I showed. And that's it. The data is not really usable for all the offline analysis you were actually hoping to do. So that's terrible. Furthermore, we at least have evidence that it's not something wrong with us. At least other people are also noticing similar issues. So there's this pretty nice paper from folks at Google about machine learning being this high interest credit card of technical debt, who point out some very similar observations. And the consequence of these observations for us is we started with this premise that we don't want to guess and check. We don't want to blindly use A/B tests and fail in our hopes to improve the system. But that's where we end up because our offline evaluation ends up being not reliable. So that's pretty bad. And it's worth asking, why is this happening to us? Is this something systematically that we're missing? And there's at least one thing that kind of jumps out. So again, let's think by analogy for a moment. So when we do supervised learning, it's pretty reasonable to think that if I took a high quality data set, if I implemented my machine learning algorithm well, and I trained the algorithm, got a model, then I should be able to just embed the model into my application without worrying too much about all of the surrounding application. I should not need to worry too much about our details. As long as I did the part of training my model well, things should work. Turns out this is a bit less true when you're solving these interactive learning problems like with contextual bandits, or this is true of many other interactive learning settings. But let's keep to contextual bandits. So there's at least a few different components that we have to worry about. So you have the exploration piece that receives a context, takes an action, right? This is the part that's interfacing effectively with the application you care about. Now, after it takes the action, it might not get the reward information until a significantly later point of time. So there has to be some reasonable logic in place to join that reward information correctly with the context action pair that you had observed earlier. And once that join has been completed, you can actually update your model. You can have your learning module update the model. And every once in a while, you want to make sure your new models are basically being absorbed by the exploration layer, because you want to have, as you learn better and better, you want to have it guide your exploration to be more and more focused. The important piece is that, the important thing to note is that each of these, at least 4 pieces that I've described here, they need to work correctly in isolation and together for the entire story that we were building in the first part to work out. If one of them fails, or they somehow do not glue together in the right way, then we have a problem. Right, so that's kind of a short overview of some of the things that go wrong in practice. And next, we're going to talk about how to try and avoid those issues. Are there any questions about the stuff we've discussed so far? Okay.
So, I have a very quick question. You
Yeah.
might cover it later. So, one of additional things we come across is the conflict of reward functions across different stakeholders involved. So, some people might care more about the click, some people might care about the conversion. So, typically in the action paradigm where we're defining policies, how to combine these different reward functions together into a single metric is also one of the problems that at least I have faced.
Right, so that's a good question. I'll talk a little bit about this again when we get to reward definitions, but one thing you can also do very practically is if there is disagreement about what should be optimized, then, you can optimize only one thing, but you can evaluate many, many things, right? You can do offline evaluation of as many things as you like. You can even offline evaluate policies that would, so you can pick one reward function, and you can do offline optimization of the best policy for that reward function, and check what it gets on several different sort of performance indicators that you might have. You could choose a different reward function, do the optimization again, offline. All of this is offline. And then again, take the best resulting policy and evaluate on various different performance indicators. And you can keep doing this till you basically find something that sort of fits some reasonable trade-off where, okay, I maybe did 0.5 times click plus 0.3 times conversion plus 0.2 times something else, and the resulting thing is actually giving me reasonable performance on every single metric that I care about. That's sort of one very practical way of thinking about how to, at the end, if you have a really multi-objective situation, then there is always some care required for boiling it down to a single number for optimization, but at least offline we can we can get pretty creative when we have multiple objectives. Okay, so continuing, what we've seen so far, based on the observations that are driving these failures, it seems like if we have different pieces that need to be correct in isolation and together, then maybe we should just try to build, instead of a learning algorithm, a learning system that drives all of these pieces together, which provides correct implementations of each one of them, but also glues them together in the right ways, so that we have a guarantee that they work together. Of course, we would want such a system to be modular, because often there is no sort of one-size-fits-all type thing here. So, for instance, the join you do here between context action, reward, information, maybe for some applications you want to use a disk-based key value store, maybe for some other application you want to use an in-memory join. So there might be, depending on application, different choices that make sense. And what you really want in your system is, as long as I assure you that I have a correct implementation of one of the pieces, then you'll put all of the different correct pieces together in the right way. Of course, we want to make the system scalable so that it can really be used at internet scale and beyond. We also don't want to over-specialize the system, so we don't want it to just work for content recommendation or mobile health applications or ad placement or something. We want to realize kind of the full breadth of applicability of Contextual Bandits to the degree possible. And finally, since so much of our grievances are about something offline and something online not matching up, we would like to build a system that is fully offline reproducible so that when we see something online that does not match our intuition, we can go and inspect offline why that thing happened. So keeping these sort of goals in mind, we've been working on a system for the last few years, which was released last year, called the Decision Service. So this has been built with a lot of fantastic colleagues at Microsoft. It comes in 2 different flavors. So there's an open source version that is available on GitHub. It provides basically implementations of all the 4 pieces you see here. You can download it. There's an easy way to deploy it on Azure. It provides Contextual Bandit algorithms to optimize things online. As you collect experiences, the experiences are recorded into an Azure storage account. And we also provide off-policy evaluation and learning tools that you can use to then experiment with that data. The only thing you have to worry about is you have to sort of host and manage the version of the service inside your own Azure account. So, if something sort of goes down, if like a VM is out or something, that's something you have to worry about. The other version of the service is a hosted or a managed version, which is available as a Microsoft cognitive service. So it's a cognitive service is sort of an umbrella term for several machine learning related services from Microsoft. It's similar in kind of the functionality, but in addition to providing all the algorithms, it's hosted by us, so we make sure that it runs on Azure, but we still want people to be able to use offline data analysis, offline experimentation, so all the experience we gather, we put into an Azure account that they can specify, and with this one, really, at least for certain types of applications, it might just be a matter of like signing up on a portal and putting a few lines of JavaScript on your web page or something to start using the service. Regardless of which version you use, we've tried to eliminate a lot of the bugs that we talked about basically by design. So a few things I want to point out. So when we get a context, when the application calls decision service with a context, and we respond with an action, we log this information right away when we make the decision. The key here is just a unique key we assign to every event. Now, at some later point, we would observe the reward for this event, and you can use this key to join them together. 2 things to keep in mind is we do this join at a pre-specified time delay. So think about clicks. Maybe some things you get to see the click on them in 10 minutes, other things maybe take 30 minutes or an hour or 2 hours. And let's say we declared that we want to do the join after an hour. So for all the things, for all the contexts where the click information is realized within an hour, exactly after an hour from the decision time, the join will happen. And if a click happens after an hour, we will drop it. It will be treated as a non-click. So this part, this pre-specified time part, basically systematically eliminates the reward delay problem. The other parts that are worth pointing out is, so here we are stashing away the features the moment we see them at the decision point. And these same features are used for learning after the join. So this issue we were seeing about kind of historical click rates being different at learning and decision time cannot happen because we stash them away the first time we see them. The other thing we eliminate is, so we log here the action that's chosen by decision service. It could happen that an editor comes later on and overrides our choice. That's okay. We can think of it as part of the external reward functional world that has basically overruled our choice. But the probability with which that is recorded in the data and the probability with which action A is chosen will be the same because we recorded the correct choice of action. Right, so this is kind of an important difference, that we are recording the action we chose as opposed to the action that was necessarily displayed to the user. Like I said, we eliminate the reward delay bias by design. We make sure we always log probabilities. Often people forget to log them, and that leads to all kinds of fun. You have to worry about reconstructing them, and that has all kinds of issues. We also use reproducible randomness, and this is kind of part of the quest to keep things offline reproducible. And there's a bunch of other things that avoid various other bugs, but yeah, I just wanted to give you an impression of why we are systematically able to address many of the failures that we've seen in the past. And the other thing I wanted to kind of point out again is, so if you do use the managed version of decision service, you kind of get this type of a dashboard for as well, where basically in real time we are doing policy evaluation for what we think decision service should be getting based on IPS style techniques, what it actually gets, and what other baseline that you might specify, something that you might have done if you were not using contextual bandits, our estimate of that thing. So that's just kind of giving you an offline estimate of how much things might be improving. Now, the even better news is that we're not the only ones thinking about this. So in the last couple of years, there have been at least 2 other systems that I'm aware of that are trying to address several similar concerns. So there is a system called Next from folks at UC Berkeley and Wisconsin-Madison. And there is a system called Streaming Bandit, released by folks at a company called Nth Iteration Labs. And all the systems provide, at the minimum provide online contextual bandit algorithms, although they differ exactly in what type of algorithms they provide. They also all have open source versions, so you can go tinker with the algorithms. You can actually implement your own algorithm if you're a researcher. You can swap out various pieces. There's, again, some details. So decision service can be, you can host in your Azure account. Next, you can host in your EC2 account. Streaming Bandit, they're not really sort of working based on any particular infrastructure. You can host it on a server under your desk or on one of the cloud platforms or whatever you like. As far as I know, the off-policy story is kind of unique to decision service. It's not something that's sort of a first-class citizen in the other platforms. And the managed version is also not, to my knowledge, provided by the other services. But regardless, it's great that we have choices. So depending on the application and the infrastructure you have, one or other choices might make sense for you. So the main takeaway I want you to have from this part of the tutorial is really there is a need to think about systems rather than just an algorithm when we are working on these interactive learning problems. And people have thought about this, and systems exist that can be used if you're a practitioner and have an application in mind. questions so far? Yeah?
So in the scenario of a human learning system which is running in parallel and taking human decisions on like suppressing policies with their own infusion-based policies, the estimate for P is going to be biased because there'll be actions taken. So that you've got a set of features, actions, P is pretty much unknown or unreliable. Or there are
So let me understand better. You're saying there is no systematic exploration. It's just people are.
There is, let's say you have a systemic exploration in the way exactly you explained, but there is also a set of human experts, like the way we discussed previously. They are taking decisions, and at times they might choose to suppress the recommendations from the decisions.
That's perfectly okay. So again, the part I want to highlight is what we are recording here is the action our service chose, that the Contextual Bandit algorithm chose. Somebody might come and override this action. So the user might see something else. And that's actually okay. Like if you go through the math, that is perfectly fine because you can effectively think of that human as part of the external reward function. So the way the reward function might look like is I choose an action, editor overrides it, and I get to see the click information on the action after the editorial override. And this does not actually break any of the theory. For instance, if the editor overrides my choice every single time, then it's actually very easy to evaluate any policy's value offline because I don't even have to think about what action policy chose. The final impact would be the same on the user.
Sure, but wouldn't it be safe when you're computing IPS estimates to just use the data that's been actually generated by algorithmic decision service and totally ignore the human learning part completely?
So you can do that. This is not always very safe to do because now you are mangling the distribution of data, and this basically means that the value you're estimating is going to be on a different distribution than the one you're actually going to see online. So that's kind of the main reason why you might not want to do that.
Okay, I have another one. So let's say you have heaps of historic data which is being collected according to a large number of biases, and you are starting to explore in a systemic way, logging and everything. So, but you want to start with some learner because you want to use that while in the
Yeah.
typically, basically, people use that learner to totally exploit rather than explore. If you want to start, is there any guidance on whether you use a simple linear learner considering your data is heavily biased by historic policies that were not systemic? Or like
So one thing, yeah, so it's pretty common that you have some observational data, you want to warm start using the observational data. There's a number of different ways you can do it. People talk about just, so in the sort of causality literature, which talks a lot more about observational data, people talk about reverse engineering probabilities, which more or less match the observed frequencies of events, and then using similar type of techniques with that. So that's one option. Another option could be you could just train a completely biased estimator anyways, and you can do something like, say, epsilon greedy or one of the other ensemble-based approaches. If you train an ensemble of different bias predictors, you can still sort of use it to at least seed the exploration, and as long as you're not learning something completely wrong-headed, that's often a pretty good place to start. Okay. All right, right, so now we have theory, we have applications, we have systems, and it seems like we should be able to hook up these systems with the applications and have fun. One of the things that arises is that there are basically translation issues. So theory says this is what a contextual bandit problem looks like. You have a problem that sort of looks like contextual bandits, but not quite. There's like some gaps in between the two versions, and you have to figure out how to do the framing so that you can leverage the techniques that the theory gives you. And I'm going to talk a little bit about some recipes for success for how to do that translation. I'm going to talk in particular about three issues that commonly arise, one to do with non-stationarity, so the world changes, one to do with the fact that you're often interested in combinatorial objects such as rankings or other complex layouts, and the third about reward definitions. So let's begin with non-stationarity. A lot of the contextual bandit literature, at least the theory parts, more or less that John discussed, rely on the assumption that the world is IID, or at least stationary, meaning that the past is indicative of the future, roughly. And often that assumption is grossly violated in practice because, so for instance, if you're doing any kind of recommendation task, your catalog keeps on changing. New news articles arrive, new products arrive, new movies arrive, and just you might not have good prior predictions of how they would do. But even if this does not happen, just people's preferences drift over time. So, most people tend to have slightly different preferences on weekdays versus weekends, mornings versus evenings, fall versus spring, so on and so forth. And not accounting for these things can actually lead to sort of sort of a breakdown of some of the techniques that we discussed so far. And that was what John was trying to show when he showed this graphic earlier, where basically, even if we take a model that's a day old for the MSN news article recommendation scenario, we lose half the value we would have collected if we were continuously updating the model. And this is actually pretty damning because these types of sort of setups are pretty common, where I collect data for some period of time, I crunch through it on a server, find a new model, update that model, and act according to it for a while, and repeat this process. And this is telling you that in many applications, that might completely kill your value. Okay, so what are some practical tricks to get around this issue? A pretty common and powerful trick is to just add features that try to reduce the degree of non-stationarity of the problem. So maybe we should have indicator features for day of week, time of day, maybe discretized to some granularity, something to do with season, and so on. And basically, if you have such features in your model, then it can learn to have slightly different preferences over actions for instance, different days of week or weekday versus weekend and so on, right? So that kind of helps. That reduces non-stationarity to some degree. One thing you have to be cautious about is when the world is changing on you, you might actually want to be slightly more conservative about how you explore. What I mean by that is if you're really thinking about being optimal in a stationary world about how to explore, then you constantly want to limit yourself to just trying out things which your past experience suggests might be good. Now, the world is changing, then even if the past experience suggests something is good, something is bad, it might become good. So you want to potentially try it out. And so often things like epsilon greedy start looking a bit more attractive in non-stationary settings. The other thing that's kind of neat about epsilon greedy, so what is the greedy part in epsilon greedy? It's really a policy that does well on the previous experience that you've gathered. And typically, what we mean by that is you take all of the experience so far, you do basically the importance-weighted multi-class classification type policy optimization that John talked about, and you take the resulting answer and use it as the greedy. Okay, but if we think that our world is non-stationary, all we can do is we can swap out our procedure for creating greedy with something that works in a non-stationary setting. So a pretty standard example of something that works in a non-stationary setting is often this policy optimization, this importance-weighted multi-class classification, might be driven by some sort of a gradient descent type algorithm. Now, gradient descent type algorithms usually use a step size that goes to 0 as you see more and more data, because if a new data point sort of asks you to go the other way, then what all the previous data said, you have small belief in that. You want to discourage that. But if you're in a non-stationary setting, you actually kind of want to respect this new data point if it's asking you to act differently because the world might have changed. So instead of using a decreasing step size, you might just use a fixed step size, with a carefully chosen constant. And actually, there is existing theory that shows that if you use this type of gradient descent algorithm, it's actually a good algorithm in non-stationary settings. Of course, you might not have a gradient descent style algorithm that you're using for policy optimization. So a very kind of simplistic hack you can do there is if you have some reasonable estimate of what the stationarity period of your application looks like. So maybe things are roughly stable for a week and then they change. Then you can just periodically restart your learning process, which is kind of a very hard version of what gradient descent is trying to do. It's trying to softly forget the past, whereas this is like hard forgetting of the past. Of course, what we saw in the stationary setting was really coming out of some very kind of nice and formal theory, and it would be great if we could have a similar type of thing going on for non-stationary settings as well, where we could formalize answers to the problem in a more satisfactory manner. One of the things you run into a little bit is that different people have different definitions of what it means to do well in a non-stationary setting, so that kind of gives you a zoo of approaches to some degree, depending on the definition you believe in. Nevertheless, there are some reasonable ways of thinking about the problem. So John talked very briefly about this EXP4 algorithm, which does some kind of exponential weighting over policies. What you can do is you can take the algorithm, which is designed for stationary environments. You can add a little bit of uniform exploration to it. You can show that it is actually a pretty good algorithm for non-stationary settings according to some definitions, which is great, except for the fact that the algorithm is not really computationally practical. So if you were just worrying about the statistical properties, this is actually a pretty good thing to do. Another kind of common approach to dealing with non-stationarity is to use an ensemble approach. So what do? You take your favorite stationary learning algorithm and you start it at different points of time. Now you're at round T, let's say, and you have to make a prediction. So you might have one copy of the learning algorithms that was started 100 rounds in the past, another one that was started 1,000 rounds in the past, another that was started maybe 1,000,000 rounds in the past. You can slap a meta-learner on top of all of these copies, and you can have the meta-learner pick which one of the copies should you trust. And that's basically like trying to find the right period of non-stationarity or right period of stationarity for your problem, except that it can be kind of adaptive. So if things keep on changing, this meta-learner can plausibly adapt to the shifting periods of stationarity. And at least one approach to build such a meta-learner was proposed recently in a cold paper we did that's referenced in the full set of references on the web page. So you get something interesting. The resulting theory is still, the guarantees are relatively weak to what we know we can do in stationary settings. So I think kind of the main thing to keep in mind here is that we have a bunch of simple fixes that I showed you on the previous slide. There's some research that actually tries to go beyond those simple fixes, but the simple fixes are extremely robust and practical, and I think there is need for these more theoretically principled approaches to get actually much more automatic and much more robust before we will feel inclined to actually use them in practice. So the second departure from theory that I want to talk about is, so in Contextual Bandits, we pose the problem as saying we saw a context, we choose an action, and we get to see the reward. And in order for the sample complexity, for the amount of data points required to be tractable, we need this number of actions to be relatively small, like 10, 20, 30, something on that order. If you're instead talking about 10 factorial, you're in trouble. But often the actions that you're trying to choose from might look like rankings, might look like slideshows or other complex page layouts, where really you might be staring at a 10 factorial or larger number of actions that you're choosing from. So if you directly try to pick over these rankings, you would be in trouble. The reason you are in trouble, like one thing that's very kind of easy to see is that when we are doing these IPS type things, we are dividing by probabilities. So if probabilities of actions get really small, we have a problem. And if you have a combinatorially large action space, you cannot ensure that everything is done with a large probability. That's just, you don't have enough probability to go around. So one common thing you can do in practice is often you have kind of a more salient location on the page, like maybe the top rank slot in a ranking or this article associated with this big image or something. You could say, I'm actually going to use my contextual bandit algorithm to just find the best choice in the salient position. So since I'm just picking a single article or a single document here, the number of actions becomes tractable again. So I can solve that problem reasonably well with contextual bandits. One twist we can have is we can use a particular type of policy class, which is basically what I might call a score-based policy. What I mean by that is I predict for every context action pair, I predict a number, which is what I think is going to be the reward if you take that action in the context. So higher is better. And then my policy is to just take the action which I think gets the highest reward. So that's a policy associated with every F. For every F there is such a policy, I can find the best such policy. And I place its action in the top slot, but then I could take the corresponding F, take the second best action according to it, and put it in the second slot, third best action in the third slot, and so on. Right? So this way I can, even though I'm exploring just at the top, I can sort of exploit everywhere. Naturally, this has some kind of obvious drawbacks. It's not really taking into account the diversity of the ranking that you're creating or the interactions between the different elements. But again, this is often a pretty good first order approximation to what you might want to do. In this case, people actually have thought a lot more about how to really do this better from a theoretical viewpoint. And partly what it boils down to is thinking carefully about what it is about a ranking that you're trying to improve. Are you trying to improve just something like the sum of clicks on the documents in this ranking? Or are you trying to improve something more holistic, like some complex measure of user satisfaction about the ranking? And the correct answer depends a little bit based on what you're trying to improve. So the simplest model that people have studied is what's called a semi-bandits model, where you think about, I have these various actions, I get to see the clicks on every individual document, and maybe all I want to improve is the sum of clicks on the entire ranking. This is kind of semi-bandits because I get to see, I get to peek into the internal structure of the ranking and get some fine-grained reward information about each element in it, not just something about the whole ranking. So people have done some, come up with some interesting techniques about how to solve problems with this structure. People have further generalized this to models where maybe you, semi-bandits is like saying that I have some intrinsic quality that's associated with every context action pair, and I get to observe it for the actions I put in my ranking. I don't get to observe it for the actions that I did not put in my ranking. Maybe I believe whatever I'm trying to improve about my ranking does break into these sum of action-specific rewards, but I don't get to observe the individual things. Maybe they are something latent. They are not just as simple as clicks. I don't know what they are. All I get to see is some feedback, some measure of user satisfaction about the ranking. I believe it breaks up into individual reward level, individual action level rewards, but I don't know what those individual things are. Turns out you can still exploit just the existence of this decomposition to actually do something interesting. Third class of models which people have looked at are so-called cascading models. It's really like semi-bandits, but thinking a bit more about ranking applications and how the user might actually be interacting with the set of ranked results. So maybe the user kind of browses the list until some point, and then if they don't find what they're looking for, they get bored and they abandon. So it's like you're getting the semi-bandit feedback, but only on a prefix of the ranking. And people have developed algorithms for this model as well. Finally, people have also tried to apply techniques from submodular optimization to explicitly worry about diversity issues in the rank lists that we are creating. But at the end, what you get is there are different models. Each model has its own modeling assumptions about the metric, about the user's interaction with the web page, and so on. And it's really down to the application that you're worrying about and what you're trying to improve, that one or other ends up being more applicable. So there's kind of more care and thinking required in picking what works best for you. Okay, so what we've really talked about so far is a set of techniques that actually get pretty effective at, given a reward function that somebody's given you, how to improve that reward function. What is that reward function? Where does it come from? It's pretty important to get it right. If you get your reward function wrong, really bad things might happen. So kind of a folklore sort of anecdote is if you're trying to, for instance, improve the revenue you generate from displaying ads, you might initially conclude that having more ads on the web page is great. And it is until users stop coming to your web page and the revenue just falls off a cliff. Now that story is actually a little bit problematic because really the part we are missing there is that we are trying to worry about something that's relatively long-term. So when you're thinking about things like revenue, what we really might have in mind is actually a quarterly profit. Or in a health application, you might actually have a weight loss target for a month or something. Or for a website, you might have a target for the number of returning users that you want to have, again, over some longish period of time. And the difficulty with all of these metrics is that they break severely the contextual bandit assumption in the sense, so in contextual bandits, we are thinking about, we have a context, we take an action, we get to see reward that's associated only and only with this particular context action pair. It does not get affected by what you did in the past, and it will not influence what happens in the future. And in all of these cases, that's just not true. Your quarterly profits are associated with many, many events that happened over a quarter. And you have no idea what degree of role any individual action might have taken in realizing this metric. So that seems bad. That seems to put us squarely into the territory of sort of this full reinforcement learning that John was trying to scare you off of, right? So can we do something while still staying in the contextual bandit land? One kind of common recipe that people end up using is for at least several common long-term measures we care about. At this point, there's pretty reasonable understanding of good short-term proxies. So for instance, if you're looking at something like user satisfaction, you might pick something like clicks or dwell time, the amount of time the user spends reading a story or listening to a song or something. If you're trying to optimize weight loss over some period, you might just try to increase the number of minutes they're exercising on any given day or the amount of calorie intake and things like that. One kind of general rule of thumb you can use is if you have a long-term reward, if you can build a good predictor for that reward, given a context, an action, and a bunch of short-term information that you can observe. So maybe take all the things about users' interaction with the web page that you can observe, like click information, the dwell time, their sort of mouse tracking over the web page, and whatnot, whatever you can collect. If you can build good predictor for the long-term reward that you're caring about, then you can just use that directly as the reward you feed into Contextual Bandits, and that can be really a pretty good short-term proxy. Some other things to keep in mind. So often there is a choice in what reward definition to use. And often you have one option, like a conversion, which is more faithful to the long-term thing you worry about, but is realized relatively infrequently. Or you have something that's more frequent, like clicks, but is less faithful. Well, if you're starting from very little to no information, then it might take you a long time to see enough conversions to actually learn something useful. So maybe starting out, you actually want to use clicks as your rewards to learn rapidly. And when your system becomes reasonably good at getting high click rates, you can start incorporating more and more of conversions into your reward, maybe through a weighted combination or using other forms. The other thing you want to keep in mind is so really, you might have a nebulous idea of what the reward should look like, but you have to boil it down to a single number. And you want to make sure that the way you translate it to a number is such that you get adequate resolution between good and bad policies that you might design. So kind of an extreme example could be if you're trying to improve the dwell time of user, maybe the best thing to do is to actually do something so offensive that they have to walk away from their computer screen for 10 minutes, right? And you get a great dwell time, you think. So it's important to make sure that you're not being driven by outliers, that you're normalizing things in the right way so that you can compare policies meaningfully. And really, the precise way you choose to encode your rewards ends up mattering quite a bit to how well you can do things. So again, as an example, we can think about, everybody probably has autocorrect that fires on their phones. You can imagine actually using a Contextual Bandit algorithm to drive those autocorrect suggestions. It's pretty easy based on what you've written so far. What should this word be? And I mean, these models are most of the time pretty accurate at predicting what you wanted to try. So we could have a reward signal that is 1 if the suggestion is accepted by the users, 0 otherwise. That seems pretty sensible. And because the models are usually pretty good at predicting what we intend to type, we'll keep on seeing the reward of 1 mostly. Now let's think about what that means a little bit for policy evaluation. So we mostly talked about the fact that IPS is an unbiased estimator, but like any estimator, it also has variance. We didn't talk about what the variance for estimating a policy pies reward looks like, but skipping a lot of detail, it breaks up into a part that depends on the variance of rewards, that's not dependent on the policy, and this part that depends on the policy, which has a piece that is reward of policy's action, and it's divided by the propensity score, the probability. And just kind of ignoring most of the detail, if the rewards are mostly 1, then you have something like a 1 over p here, right? Which is bad because probabilities might be small, so 1 over p is going to be large, which means we are going to keep paying a lot of variance in policy evaluation. If you know that something is going to be 1 most of the time, if only you could make it 0 most of the time, then this part goes away, right? So that seems like a better choice. Turns out it's actually pretty easy to arrange that situation by just saying, oh, I get a 0 if I choose the right suggestion, and I get a -1 if I choose the wrong suggestion. I didn't change anything fundamental about the problem, except this variance goes way down. Just one example. There are systematic, by the way, learning techniques like W-robust that John only briefly flashed on a slide, which are also supposed to help with these large variants. But in general, you can either have something that's carefully learning about how to reduce the variance of estimation, or you can choose a smart encoding by hand by thinking a little bit about your problem. Generally, if you choose a better encoding, you'll end up being more data efficient because you don't have to spend data learning that. Right, so that's something pretty important to keep in mind. So the final thing to remember is, yes, there are gaps between how the theory describes the problem and how the problem appears in practice, but we have some pretty decent recipes for how to address these gaps, at least in common scenarios. Now, I know it's getting late in the day, so you might start getting worried that, wait, so, okay, first of all, I need systems because otherwise things fail, then I have to do all this problem framing because things don't quite match up with theory. So, you know, if I have to do so much work, will this stuff actually work at the end of it all? That's a legitimate concern. So in the final few minutes, I'm going to show you just a glimpse of how things might look if you do all the work we described so far, how you might actually benefit. And I'll sort of do this as a demo. So we'll be using data from a website that uses this decision service system that I described to you. This website is complex.com. Quite popular among millennials in US. And they use decision service to pick news articles in the slots shown here and several other parts on the web page. I'm going to take data from this website. I've modified all of the click information by monotone transformation because I cannot actually reveal their real click-through numbers. So let's start with first what the data looks like. This is data that actually decision service collects when it's exploring and provides in your in an Azure account for offline analysis for you. And there's some high-level information that's available. So the data is in JSON format. There is some high-level information about, here's a record, what action did we choose on this event, the probability with which we chose the action, the observed cost. Again, we are operating in a cost rather than reward basis here. There is the unique key I said we associate with every event. And then there is the context, the features. So we have a bunch of features about the users, such as where they come from, how they arrived at complex, at the articles. Were they directly going to the website? Were they going through a Facebook link or something? And what's their user agent, so their browser device, etc. Because our actions actually are these rich news stories, we also have a bunch of features about each action. So actions have these images associated with them. So some of the features have to do with maybe what are the objects I see in the image. Maybe I recognize some celebrities in the image or in the article. Maybe I can do some basic emotion and sentiment analysis on the article and so on. So that's what the features look like. We can take this data and we can start asking these offline evaluation questions John talked about with this data. So the first thing we're going to see is, so the first part is going to be about policy evaluation, which means we're going to use the progressive validation technique. And the first thing we can do is, so I'm going to start and then talk through what's going on. Okay, so we'll come back to the numbers in a moment. So, so what we provide is we provide our users, in this case Complex, with a way to specify what they would have done if they weren't using decision service. And in this, we are just evaluating using this data set that I have from Complex, how much value does that policy generate? And we do that, and we get we do the progressive validation of that policy, and we get a number that's here. Okay, so this is a monotone transformation of the click-through rate that the policy gets. So now we can, rather than using this this policy that they provided, we can take the features we have and we can start learning some sort of parameters, a parameterized policy over those features and ask how much value can we generate that way. And that's what we're going to do in the second part. So I'm going to start that experiment and then I'm going to talk you through what's going on. So, so let's parse this command line slowly. There's the data set. This flag CBADF indicates to VW that I'm trying to solve a contextual bandit problem, and I have a data set where there are features associated with different actions. So we saw that we had different articles had different features associated with them. It's just saying my data is in JSON format. This bit is interesting. So like I said, we worry about non-stationarity in the problems, and often that means we do not want to drive our step sizes in gradient descent to 0, and that's what this power T0 flag says. And this second flag says that this is the actual value of step size, the non-decaying step size that I want to use. Finally, the policy class. So I'm going to use a linear policy. One thing I want to highlight is, so here, as you can see, there are different groups of features, and each sort of group starts with a capital letter. So that we use that letter to basically refer to that group in this command line. And what we are saying is we want to use a linear learner, but that uses some pairwise interaction features. So I'm going to take the features about the user geography, and I'm going to interact them with some tags I extracted from the image associated with the action. I'm going to take the referring URL that the user came from and interact that with the emotion that I extracted from the article and so on. Okay, so we run policy optimization over this policy class. Again, progressive validation keeps on reporting the value of the best policy it's finding at different points of time, and eventually it concludes with a number, and the number is easier to see over here. So there's quite a bit that we managed to gain by using a carefully chosen parameters with good features. The second thing we could do is we talked about evaluating exploration algorithms using rejection sampling type techniques. So we could do exactly that. So I'm going to, once again, start that evaluation. Okay, so let's come back to this. So the first flag here indicates that we want to basically evaluate an exploration algorithm and use this rejection sampling type technique, which is different from the CB flag we were using before, which was just trying to do policy optimization. So that's this. The rest of these flags, everything about my policy class and my step sizes and so on remains unchanged. The only other thing I indicate is the exploration algorithm I'm trying to evaluate, which in this case is epsilon greedy with uniform random 10% of the time. So again, I mean, evaluation looks pretty much the same. You're getting a number with progressive validation. One thing you might notice is that the numbers look a bit smaller now, because previously you were just worrying about what would happen if you could exploit all the time and somebody gave you high quality exploration data. Now you're actually taking into account the impact of exploration, which obviously leads to a lower click-through rate. But since we know that things better than epsilon greedy exist out there, we could actually swap out the exploration algorithm for something else. And again, that's pretty easy to do. Just replace our choice of exploration algorithm. And here we are using something that was proposed in this 2014 paper we did and is known to be statistically and computationally optimal in a certain sense. Again, we didn't really change anything else about the policy class or the features or anything. And takes a little bit longer to train because this is an ensemble approach, so it actually, rather than training just one policy, it trains actually many different policies to build an ensemble over. So that's a good observation. I think what you're looking is that the epsilon here has been reduced to 5%. So the reason for doing that is here I'm building an ensemble of 4 policies. So that is already giving me some exploration over good actions. I still require some amount of uniform exploration mixed in, but I want that to be much smaller now.
Over time, as we learn, it's expected to even go smaller.
Yes, so depending on, so if you were in a stationary setting, you would just decay it to 0 over time. In non-stationary, you have to be a bit careful. But yeah, you again see an improvement. And again, the actual magnitude of the improvement is meaningful up to a monotone transformation. But I think more important than even the numbers here is the fact that we could take all of these ideas, take a data set that we had on our computer, and we could just evaluate those ideas, which is very different from if you have to do something for an A/B test, you have to create actually your idea until a point where you have production-ready code for it, then you can deploy it, and then you get to observe what's happening. And here, in a matter of seconds, we can evaluate many different ideas. So that's really the highest level point I wanted to take away from this. Okay, so running out of time, I think the main message we wanted to drive from the tutorial is we've reached a point in contextual bandit research where a lot of the basic ideas have matured, and really the techniques are, to a good degree, fit for broad consumption. There remain some questions which require further research, but you can actually go a long way with what's already available. Definitely, you can go a lot beyond what you get with supervised learning, and things are fairly, are much more easy than general purpose reinforcement learning. There's room to definitely do more research in terms of creating more automatic and parameter-free algorithms. We've found one subset of reinforcement learning where things work well. We would like to obviously extend it to broader and broader subsets of reinforcement learning. And finally, if you're a practitioner and application developer, then just like supervised learning becoming automatic was kind of a watershed moment for applicability of machine learning, this is a new set of techniques that is becoming more reliable, more robust, more usable, and you should feel really free to use it in all kinds of exciting ways in applications you care about. And to conclude, to sort of get people's creative juices flowing, I'll end with a particularly fun and useful application that some people at Microsoft worked on as part of a hackathon. So what they were trying to do was, so they put these EEG headsets on people, and they were trying to see if we can basically learn how to type using just the EEG signal. So there was some initial supervision phase where people tried to sort of indicate, oh, this is the gesture that's sort of associated with this character. And the system can learn that okay-ish. So then what they did was, because different people kind of do the same gesture in slightly different ways, and especially if you have some handicap, then the differences can be even more pronounced. So they decided they're going to tailor that learning to the user using decision service. So that was kind of the second phase. And they managed to get things working reasonably well. There's a video that shows how things work out. So yeah, that's, this is just a hackathon prototype. So I'm not saying this is something that's ready for broad consumption, but just to give you an idea of the scope of applications. A lot of this research has involved a number of fantastic collaborators. We are just explicitly calling out the various people who were involved in writing the papers that have been cited through the tutorial, and there are many more that have actually inspired the thought process going into this research, and we're extremely grateful to them. I'm going to pause for further questions. And again, like John pointed out, we're going to put all the slides and the detailed references are also available on the tutorial webpage on hunch.net. Thank you.